In this video, after we have derived the spring element stiffness equations and the spring element stiffness matrix, we are going to move to step number 5, where we are going to assemble the element equations to obtain global equations. So we are going to look at two spring assemblage. I have a spring 1 that has the stiffness K sub 1 that is connected to a spring 2 that has a spring constant K2. Now, if I look at this assemblage and I'm going to consider my discretized system, I would consider 3 nodes and 2 elements. So the first element of spring 1 has a stiffness K1 and extends between node 1 and node 2. The second element, element 2, that has a spring constant K2, extends between node 2 and node 3. This system is fixed at A, and we do have applied forces at node 2. I have an F2, and at node 3, I have an F3. And the springs are oriented along the x-axis. And so this F3 is oriented along the x-axis, and this F2 is oriented along the x-axis as well. And I can mark here that this is element 1, and this is element 2. So node 1 is fixed, and axial forces are applied at nodes 2 and 3. The x-axis is the global axis of the assemblage. So we are going to start by writing the element stiffness equation. So for element 1, I'm going to show here my element. So this is the element 1, has a stiffness K1 and is between nodes 1 and node 2. My nodal displacement would be U1, element 1, and U2, element 1. Sorry. And at the nodes, we do have nodal forces. So I have here F1 in the x direction. Sorry, this is the F2 in the x direction applied to element 1. And here I have at node 1, I have an F1x applied to element 1. If I want to write the element stiffness equations, I can put it in matrix form as F1x element 1, F2x element 1 equals to my spring stiffness matrix multiplied by the nodal displacement U1 element 1 and U2 element 1 also. My stiffness matrix would be a K1 minus K1 minus K1 and a K1. We're going to repeat the same for element 2. So this is the element 2, has a spring constant K2, connects between node 2 and node 3. At node 2, I have the nodal displacement U2. I also have a nodal force F2x applied to element 2, and this U2 is specific to element 2. And at node 3, I have also have a nodal force F3x applied to element 2. So I can write my stiffness equation. F2x element 2, F3x element 2. This is equal to my stiffness matrix multiplied by the nodal displacement. I get U2 element 2 and U3 element 2. And here I have for my stiffness matrix a K2 minus K2 minus K2 and a K2. Now element 1 and 2 must remain connected at the common node 2. In order to maintain this at common node 2, then really U2 element 1 must be the same as U2 element 2, or we can simply say equal to a U2. This is called the continuity or compatibility requirement. Next, we look at a free body diagram of the assemblage. So I'm going to set the elements free, and I'm going to show all my forces. So I'm going to start here with showing my element 1, and here my element 2. Node 1, node 2, node 2, and node 3. And when I'm looking at a free body diagram, I'm going to be looking at the forces. So I have the nodal forces on element 1, and they're all in the x direction. So I have this F1x applied to element 1, because this is the element 1, and this is element 2. And here I also have an F2x applied to element 1. At node 2 of element 2, we have an F2x as it applies to element 2, and at node 3, we have an F3x applied to element 2. If I start looking at the nodes and the equilibrium of the nodes, if I look at node 2, it is subject to the equal and opposite of F2x element 2, equal and opposite of F2x element 1, as well as the externally applied force F2. We are going to do the same, look at the nodes 1 and 3. So if I look at node 1, I have the equal and opposite of F1x element 1, and I also have the external unknown force or reaction force F1x. Please note that this is an uppercase. When an F2 also here, this F2x is also an uppercase. When I look at node 3, I have the opposite here of F3x2, and I have the externally applied force F3. Now we can write the equilibrium nodal equation. So I look at each node and write an equilibrium equation. So I'm going to look at node 1, and at node 1, I can say that F1x is equal to F1x of element 1. If I look at node 2, we can see F2x is going in the positive x direction, and these lowercase F2x1 and F2x2 are going in the negative direction. So I can say F2x must be equal to this F2x element 1 plus F2x element 2. And when I look at node 3, I can say that the uppercase F3x, here, this is F3x, is equal to F3x element 2. Now I'm going to use my element stiffness equations to substitute for F1x. So it's applied as element 1. So I can see here that this is equal to a K1 U1 minus a K1 U2. For F2x, I'm going to use my element stiffness equations for element 1, and I'm going to say this is equal to minus K1 U1 plus K1 U2. So this is F2x element 1. But then I also have a plus, and I get to F2x element 2, which is going to be a K2 U2 minus K2 U3. For F3x element 2, I'm going to come here and say this is equal to, based on the element stiffness equations for matrix 2, is equal to a minus K2 U2 plus a K2 U3. If we combine this nodal equilibrium equation with the element force displacement stiffness relation, we can obtain the global relation. And I can establish these by putting here F1x, F2x, and F3x. And please note that these are all uppercases. These are equal to. And here I have my global stiffness matrix. And now we only have one U1, one U2, and one U3. So these are the global nodal displacements. F1x, we had a K1 U1, and we have a minus K1 U2, and we don't have anything in terms of U3, so I put a 0. For F2x, I had a minus K1, I had a plus K1 U2, and I also had a K2 U2, so I'm going to put a plus K2 U2. I also had a minus K2 U3. For F3x, we had a 0 in terms of U1, and then we had a minus K2 U1 and a plus K2 U3. This takes the form F is equal to K times D, where F is the global nodal force matrix, and D is the global nodal displacement matrix, and K is the total or global or system stiffness